Okay, so we might as well get started. So last time we ended up starting the discussion on how to apply either boundary conditions or jump conditions across an interface. For example, you may have a vaporizing droplet, and this droplet may be stationary, with the exception that the surface of the water is moving down as the water evaporates. And now we need to know for the gas phase side is what is the velocity of the gas coming off of that surface, or of the vapor, I should say. And so to find out that information, we need to use what's called an interfacial control volume analysis. Okay, and so recall that we had a standard control volume like this. It's designed to follow the surface for a short segment, and it's designed to be extremely thin. And in the analysis, we make the height on the side here tend towards zero, but it's not exactly zero. So basically, you could imagine this as being extremely zoomed in, and but yet the top of the control volume is just barely in the gas, and the bottom of the control volume is just barely in the liquid. And in a sense, this is sort of what you the same style of control volume and very similar arguments that you make for those of you who fed compressible flow or gas dynamics, when you are drawing a control volume around your shock wave and you're deriving the properties for that. It's it's a very similar concept. Okay, and so here I'm just going to label the two materials as plus and minus. It could be gas over here and liquid over here. Okay, and so we just, to get an idea of how this works, we basically are going to modify the RTT, where we are transporting an intensity or an intensive quantity B, which is just a generic intensive property. It could be velocity, it could be internal energy, etc., etc., mass fraction, all kinds of things. Okay, and I'm going to define n hat. It's the direction you pick is arbitrary. It just matters that that you are consistent. Is that n hat points towards the plus side, and also we can have some fluid flowing in and gas coming out, and also the interface can also be moving independently of that stuff too, if there is some sort of phase change or combustion going on the surface. And so I'm defining the surface to move at velocity vi, and it could be going up or to the left or to the right, and that's the absolute velocity. Okay, and so that is not with respect to the surface. In my derivations here, I'm going to define that to be the absolute velocity of the surface. Okay, so now we got this control volume here, and I wish the iPad was big enough that I could fit both the full control volume and the RTT on both, or on the same screen, but unfortunately iPads are not big enough for that. So we apply the RTT, which is the same one that we used for the deriving the governing equations. And so this is essentially the same, except for now we are defining the control volume to follow the surface. So that means that the boundary velocity of the control surfaces is defined to follow the interface. Okay, and so the boundary velocity, because the CV follows the surface. Its boundary velocity on the top and the bottom, and the sides for that matter, are the same as the interfacial velocity. Okay, so are there any questions?
Professor, just a quick question. Does epsilon change? Like does the size of the CV, even though it's like infinitesimally small, does it change, or is it because the surface as it moves, could it deform so that the CV would change, or
No, we don't. In fact, we take the limit as epsilon goes to zero.
okay.
Yep. So actually, just to answer this question, so we we want a very thin CV, and we're going to take epsilon approaching zero. But as I said before, it's just barely large enough that the top and the bottom are basically in different materials. Okay, and so and this epsilon here, it's going to tend towards zero. And even though it is non-zero, as this sort of surface recedes and moves down due to evaporation or combustion of a propellant, it's basically going to move down. This control volume will maintain its exact shape as long as the surface doesn't change its shape, and it will basically move down with it. Okay, are there any other questions? Okay, so now we're going to take the limit of our RTT as epsilon goes to zero. Okay, so we are going to do that. And if epsilon goes to zero, we can basically work out our surface integral in the normal fashion. So we just got the contribution from the top and the contribution from the bottom of the quantity of B flowing through it. That would be these two terms right here. And notice that if epsilon is going to tend towards zero, the cross-sectional area on the sides is going to be zero, or that's also going to approach zero, or at the very least, it's going to be extremely small in comparison to the flow through the top and bottom of of uh, uh, of the control volume. So that basically means that as epsilon approaches zero, we can actually forget about the fluxes all the fluxes that are going through the sides, okay? Because they essentially are going to have zero area. So if we are to expand the surface integral into all four of its terms, we have the top, the bottom, and the sides. And the sides are small relative to the top and bottom. So our surface integral just basically turns into the difference in the fluxes going through the top and the fluxes going through the bottom. Okay, and so that should be, if you sort of think about it from just drawing the standard control volume, that should be fairly intuitive. Okay, and so I'm going to define the velocity in the normal direction because we have all these v dot n hats. I'm just going to call that un. And also for the boundary velocity, or the interfacial velocity, we normally only care about that in the normal direction, with the exception of one term. And so for the boundary velocity, I'm going to define UNI, which that's just VB dot n hat. And so that's the absolute velocity of the surface in the normal direction. Okay, are there any questions? Okay, so putting everything together, we can actually work on these dot products here and substitute in all my definitions here into this. And we wind up with this expression here where we have just our surface integral term here is just rho plus b plus times the quantity un plus minus uni times a minus rho minus b minus times un times the normal of velocity on the bottom of the control volume minus the interfacial velocity. Okay, and these are all multiplied by some area A. In most cases, we will not need to know what that is because it will basically cancel out. Okay, so finally, our modified RTT is this here. We can actually, and again, this works for just about everything. And in general, it looks like in 99.9% of cases, this integral here of ddt, of the integral of the volume integral of rho b dv, most of the time, with the exception of two terms, that goes exactly to zero, because there is simply no volume in which to integrate a quantity. The two exceptions to that are are baked into the species mass uh, equations when you have activity going on exact only on the surface. And so in those cases, this term is not zero, and we need to work with it a bit. But for our applications, those terms that you get, you normally don't need to worry about. Okay. So are there any questions with this? So our modified RTT that we apply to our generic control volume is basically just this. Okay. So now, like we did before, we start applying this RTT to the various conservation principles. And so we'll start with conservation of mass. Okay, and with conservation of mass, recall that in the RTT, that B is equal to 1. Okay, and so for conservation of mass, that's pretty straightforward. So we apply this equation here with B equal to 1. Okay, and so B here is exactly equal to 1, and so we just basically substitute in B equal to 1, and we get this expression here. And note, so this here is the volume integral of mass over the entire control volume. And if we are making epsilons go to 0, that means there is in effect no volume inside this control volume. So basically, the integral of something that has no volume, or the volume integral of a quantity where there's no volume, is going to also approach 0. So that means in our very thin control volume, there is essentially no mass inside of it, and because it's so thin, basically all the flux is going, the net flux is going in through the bottom must be equal to the net flux is going basically going out through the top, at least for conservation of mass. Okay, and so that means the control volume is so thin that it is basically always in steady state conditions, at least as far as conservation of mass is concerned. Okay, so are there any questions with that?
Yeah, I just have a question real quick about the thinness of the control volume. So I'm assuming that we still have our continuum assumption, but do we just have continuum and like along the length direction of the control volume, or?
Yeah, that is sort of a tricky, almost philosophical point, is that when with an infinitesimal control volume, it's implicitly large enough that you're not violating the continuum approximation. So it's sort of tending towards 0 in the sense that it's tending towards 0 volume, but it's not so small that that you're violating the continuum approximation.
Okay.
Okay. Okay. So we get rid of, so based on the epsilon going to 0, we can get rid of this mass accumulation term. And we are left with just a balance of the mass flux out through the top and in through the bottom. Okay, and so we can actually rearrange this. I'm just going to move this to the other side, and we have A here and here. So the cross-sectional areas basically cancel out. And so what this says is that the mass flux, I'll draw the control volume. Oops. What this says is that if we have our surface here and we have our control volume, is that because it's so thin, all of the unsteady effects inside the control volume are negligible, and it's basically saying that the net flux in through the bottom has to equal the for conservation of mass to be satisfied. It means that the net flux out through the top has to be the same. Okay, and that's basically what this is saying here. It looks a bit more complicated just because we need to account for the fact that the surface may be that the surface may be moving at a different velocity than the material. Okay, and so but do not be intimidated by this extra term here. Okay. And so this here would be conservation of mass at an interface. Okay, and so I'll just go through an example of how we use that. So we are going to consider a gas-liquid interface. So we have gas on top and liquid on the bottom. Gas will be what we label as the plus fluid, and then liquid will be the minus material. Okay, and so we are going to assume that the liquid is evaporating, and that due to evaporation, the surface of the liquid is moving down at some velocity RB. In propellant combustion, that RB you're gonna see that a lot. That's called a regression rate. Okay, and so I could have called this a burning propellant and said that the surface of the burning propellant is moving down at RB, and then that would also be and that would also apply. And so we are going to apply, and also we're going to assume that the material on the liquid side is stationary. And so that means that basically that means that the normal velocity, basically un minus, is equal to 0. And we are defining our surface to be moving down at some velocity RB. And so basically UNI is minus RB, because again, we're defining the positive direction pointing up into the positive fluid. And so the negative, and it's moving down in the negative direction. You know, intuitively, it's an evaporating fluid. The surface as it evaporates is certainly not going to move up. That would mean that would be backwards. So there is some intuition that basically when you're defining these, and basically what basically what the normal velocity is, and things like that, there is a little bit of intuition that you will need to apply to fully solve these. But if you say assume RB was to go up for an evaporation problem, that would be that would probably come out. It should be, if you were to make that mistake, it should be fairly obvious that you made that mistake after you work through, say, conservation of mass, and you realize that everything is backwards. Okay, and so, but there is some intuition that you need to apply for this. Okay, and so, and then in solving this problem, we are going to pretend that we know the density over here and the density over here. So we know rho minus and u minus. So we and we know rho plus, and what we want to find is u plus. Okay. So what we do then is we take our expression over here for the conservation of mass balance, and we then substitute in basically minus RB for the normal velocity. So we have minus RB. We substitute that into here and here. Okay, and we have that basically UN in the minus direction is 0, and we don't know what that is. So I'm just going to leave that alone. And so we basically have this expression here. So I basically substitute them in. This UN is equal to 0, and we wind up with plus RB. Here, I'm just going to label this as m dot double prime. This here is an evaporation mass flux. You'll see the quantity rho RB quite a bit, especially when we get to propellant combustion, and that's nothing more than a vaporization or a burning mass flux. Okay, so, and commonly you'll see the expressions that I'm going to derive actually written in both forms, with m dot double prime or a regression rate. Okay, and so I'm going to work in regression rate form, and I'm just going to solve this. For our gas velocity leaving the surface. And so I'm just basically applying some light math here. So basically UN plus is equal to the ratio of the liquid density to the gas density times multiplied by the regression rate and minus the and minus the regression rate. Okay, and so I can factor out RB here, and I get this expression here. And notice that even though the absolute velocity of the liquid is stationary, there is a non-zero velocity of the gas leaving the surface. Okay, which actually I should correctly say as vapor leaving the surface. And so this here is commonly referred to as the Stefan velocity, and it is a blowing effect that is caused by phase change. Okay, and so even if the liquid is stationary, just due to the fact that as the surface, as it's vaporizing, the molecules are expanding in volume by a factor of 1,000. Okay, so the density here is roughly 1,000 times, basically 1,000 times smaller than it is over here. And so if the net if the net flux relative to the surface has to be conserved on both sides, that means that the gas, or that the gas vapor is going to accelerate to on the order of 1,000 times higher than the liquid. And so that's what this term here is saying, and we subtract off an RB because our system is actually moving down with the fluid, or is moving down with the interface. So we do need to subtract that small bit off. Okay. So are there any questions with this? Okay, yeah. So now we've done conservation of mass. I've done an example with that. And so species mass is probably one of the more tricky equations to work with. So for species mass, we have our B parameter equal to yi. But now in our conservation law, we had that the right-hand side was not equal to 0 like it was for mass, because recall for conservation mass, we had dm dt equals to 0. So which means the only terms we had to worry about for conservation of mass were just the terms in the Reynolds transport theorem and nothing else. But for species mass, we have we can have chemical reactions going on inside of the volume, and we can have also a mass diffusion fluxes going on the surface. Okay, so if we draw a control volume of a species I, and we'll just pretend that's a gas phase species, and that's another gotcha with species mass, is that in general, species do not exist in the same form on both sides of the interface. So if you're dealing with a gas phase species, a common way to do this is to only worry about the gas phase side of the control volume. Okay, and you can still consider the both sides of the control volume, but in effect, you are really only caring about what's going on the gas phase side. And the reason that is because say you have, say, a droplet of water here and air over here, is that basically, like, say, nitrogen does not exist inside of the droplet. Okay, and so it basically makes no sense to conserve species mass of a species that does not exist inside of the droplet. Okay, but also you can see that if you are a chemical engineer and you're worrying about like dissolution and things like that, then you may have to worry about that stuff. So species mass is probably the conservation law that gets a little bit tricky for an interfacial control volume. I mean, you really have to think about your basically quantities. Okay, and so if we have our gas phase species here, we can have yi minus is equal to 0 because it exists only in the gas phase side. So we have in our control volume, we have that species mass rho plus un plus yi plus leaving through the top. We have a diffusion velocity. So we have rho plus yi plus times vi. That's the diffusion velocity. And also, we have a chemical reaction, and I'll derive this formally. But essentially, we do not need to consider chemical reactions occurring in the material itself, but we can have a surface reaction. And a surface reaction is a reaction that occurs exactly on the surface. And so we need to account for that. And so an example of a surface reaction would be evaporation. And I have some down here. So an example of a surface reaction would be, say, in your car, you have a platinum catalytic converter. And so for a surface reaction, how those work is you have nitric oxide, and you can also have CO2. They basically impact the surface. The surface acts like a catalyst, and essentially you could think of these sort of nitric oxide molecules and CO2 molecules basically impact the surface, basically stick on, and they kind of roll around a bit, and then they collide on the surface. And then what comes out after then basically what comes out after the chemical reactions are actually nitrogen and CO2, which basically then detach from the surface. And so all of this chemical reaction that is converting NO into N2 and CO2, that is a surface reaction. That is a reaction that is occurring only on the surface. Another example, I think, would be an oxidation of a carbon particle. So there, one mechanism for that is you have an oxygen molecule going on to and attaching to the surface. Then after some time, it reacts chemically, and it produces a CO. And as it produces the CO, basically the oxygen molecule has attacked the carbon graphite, and it basically tore out a small chunk with it. Okay, and so those are examples of surface reactions. And so these processes occur only on the surface. They do not occur in the volume above or below the surface. And so we do need to account for those in our control volume. Okay. Okay, so are there any questions with that? Okay, and for the case I have drawn here, species I, D and E means does not exist in the minus side. You can have species you can have a species that exists only in the minus side too, or you can have species that exist on both sides. And so for species mass, you really need to think about the equations, okay, and think about the physics. So we're going to apply our RTT. And so we have the limit as epsilon goes to 0. And again, I just did the full RTT here. And we have this extra term here due to the surface integral of the diffusion velocity leaving the surface, and the volume integral of the chemical reactions. Okay. So as I sort of argued before, in general, species can stick to the surface. And these surface species exist only on the surface. And so when we want to describe that surface, I'm not going to get into surface reactions in this class. But if you work in engines or say gas turbines for power generation, and you're working on after treatment of the combustion products, you may have to worry about surface reactions. Okay, but basically here, when the nitric oxide basically stuck to the surface, there is a separate species of basically the surface concentration of NO on the surface. And so that's called a surface species. And basically it is a density per unit area, actually not mass, area. Okay, whereas normal density is the mass per unit volume. the surface density is the mass per unit area. So you could think of it as a surface and you have a bunch of molecules and you can only have so many molecules basically stuck onto the surface at once. Okay. Okay, and so in the volume integral here, in the volume integral here, there's no, we're going to take the control volume again to be very small, so there's no mass above or below, or there's no change in mass, or there's no mass above or below, but we do need to consider in general, even though in this class we are never going to work with it, we do need to consider the fact that you can have species accumulating on the surface, basically for those type of surface reactions. Okay, and so what we do is we replace rho y. You can replace rho yi in the accumulation term, which is this term right here, with the site density of species I times delta times x minus x interface. And again, we are defining x to be the coordinate system attached to the surface. And so this this delta here, which some of you may or may not have seen, is called a Dirac delta. And delta is 0 if x are the argument of or if the argument of Dirac delta is not equal to 0. I should probably change that to some other dummy variable, z. Okay, and so it is non-zero only if this argument is exactly 0. And you may think, okay, so, and it's defined such that the integral of the Dirac delta function between minus infinity and plus infinity is exactly equal to 1. And so what we're doing here is we are replacing the standard rho times yi with the site density of the species, and we are multiplying it by this Dirac delta function that is 0 by definition on the surface. So basically what this and the integral of this Dirac delta function is 1. And so basically what this is doing is that is setting up a scenario where in the volume integral of rho yi, if we substitute in for rho yi, basically rho y double prime times the Dirac delta, this Dirac delta function is non-zero only on the surface. So that is basically forcing our volume integral to be non-zero only on the surface, and we know that the value we know the value of the integral here is 1. So it's and so what this is in effect doing is this is selecting only the surface. And so basically what we are doing here, what this Dirac delta function is doing, is it is turning the volume integral into a surface integral. And so that is another way that that you can turn a volume integral into a surface integral. And in Kuo's textbook, which again you can get the low price edition for $30. He does go over this a bit more. I'm just basically bringing this to your attention that you do see this being used from time to time, especially when we start to track interfaces for basically multi-phase flow and combustions. And you'll basically be using this trick quite a lot, where you'll be multiplying something by a Dirac delta to integrate, and then integrating over the whole volume of that quantity if you want a surface integral, because sometimes it's really difficult to define exactly what a surface is. So you can just do it sort of crudely by multiplying it by a Dirac delta and then integrating. Okay. So basically what this does then is this means that the limit of rho yi times the volume integral as we take epsilon goes to 0, again, as we make epsilon or these sides go to 0, is again, we are only removing the portion of the control volume where the Dirac delta function is exactly 0, which means we are not changing this integral as we make epsilon tend to 0, because the Dirac delta function is exactly 0 or exactly non-zero only on the interface. So that means we've turned our volume integral into a surface integral. Okay, and so basically we turn it into the surface integral of the site species. Okay, and we can do the exact, so if you want to figure out where the surface reaction term comes from, you can do the exact same game for the chemical reactions. So again, the volume is too small for chemical reactions to be important in the volume above or below the surface. But again, they can occur on the surface. So we replace the volume integral of omega dot I dV, which is the chemical reaction rate for species I, and we just replace that with a surface reaction rate, again multiplied by our Dirac delta function, which basically picks the surface. Okay, and so basically what this means is that we turn our volumetric reactions. We apply the exact same game, and we turn that into a surface integral of just the surface reactions. Okay, and note, since these are technically a flux, it is understood to the mass flow produced by a surface reaction is understood to be normal to the surface. Okay, so are there any questions with that? So in really formal mathematics, that is what, if you start from the basic conservation laws, that is what allows us, that is what allows me mathematically just to write an internal generation term, omega dot I double prime, that is occurring on the surface. Is basically, it comes from that mathematical trick. Okay, and so again, if you want more information on this step, there is slightly more information in Ken Kuo's book, which again, you can pick up for $30. Okay, so now we put it all together. We got to consider the diffusion velocities. We don't have to do anything fancy with those. So if we put it all together, we have the accumulation of species I on the surface, plus the net flow out through the top, minus the net flow in through the bottom, is equal to the diffusion velocity in through the bottom, minus the diffusion velocity out through the top, plus the generation of species I on the surface due to surface reactions. And that could be either phase change, evaporation, or actual combustion of a carbon particle or combustion of a solid propellant. And we'll be dealing with all of those later on in this class. Okay, and I'm defining V and I as the normal component of the diffusion velocity. So that's just the diffusion velocity of species I dotted with n hat. Okay, and so putting it all together, we have this expression here. Okay, and so this here is general. It would apply to really anything, a catalytic converter, or a burning chunk of propellant. Okay, but normally for our combustion applications, this the site species accumulation term is negligible, so we don't need to worry about it. And so that goes, and so we can basically make this tend towards 0, and we wind up with something more familiar. Okay, and so basically this here is a standard, almost a standard conservation of mass balance, with the exception of we have a mass fraction here, and I've pulled in the diffusion velocity into these terms here, and we have a generation term on the surface due to surface reactions. Okay, and so this here looks pretty formidable, and this here is a bit more straightforward to work with. Okay, but you still really need to when you solve problems with this, you still really need to put some thought into thinking about what basically what the mass fraction of species I is in the liquid side versus the mass fraction of species I on the gas phase surface, and what the surface reaction rate would be if there is one. Okay, and often the surface generation term needs to be modeled, and so if for an inert surface for species I, omega dot I double prime is equal to 0. Okay, because basically we are not generating any species. Okay, and so we could also have a surface reaction, and so here we could have carbon graphite plus oxygen goes to CO, and that is occurring on the surface. And so, and I already described this one, and in the context of combustion, it should be clear why that one is important. Now, for these surface reactions, more often than not, their reaction rate depends only on the gas phase concentrations. So a reaction rate would be a Fourier rate constant times the concentration of oxygen. It is normally not multiplied by the concentration of carbon graphite. Okay, because that quantity is not really changing, because again, it's occurring only on the surface. And so you could think of the concentration of carbon graphite near the surface is not changing. Okay, and so a reaction rate for surface usually for the law of mass action, you apply only the gas phase species. Okay, and then but you do need to consider it in the rates of production. So if you apply if you convert this to a mass rate of production for the carbon, CO2, and O, and apply the equations that I showed a few weeks ago, you would basically get this. Okay, and so that would be how you'd handle a surface reaction. If you have evaporation, and the term diffusion limited, we will talk about that when we get to multi-phase combustion. But you would need a model for this omega dot I double prime. And so one way to do that is to use what's called, there are lots of ways of doing that. One way that works quite often is called the Schrage-Knudsen equation. This comes from the kinetic theory of gases. Okay, and that would basically be the evaporation mass flux is equal to the production rate of vapor. I don't know why I have a minus sign there. And basically it's just equal to this expression here, where P is the saturation pressure. And basically it's what is driving the evaporation is the difference between the saturation pressure of the vapor on the droplet and the partial pressure of vapor on the gas phase side. Okay, and so if they are out of balance, there is a net phase change, and it predicts both evaporation. If this term is greater than 0, you have evaporation, and if it's less than 0, you have condensation on the surface. Okay, and so the C here is called a condensation or evaporation coefficient. And there is data on that for say water, but even for water, there are 3 decades of data scatter, so the measurements are unreliable. So if you wind up needing to use the Schrage-Knudsen equation, there is a nice curve fit correlation based on some really nice molecular dynamic simulations from Nagayama and Tsuruta. Okay, and so if you wind up ever needing the Schrage-Knudsen equation and you don't have reliable data, which is more than likely the case for the condensation coefficient, you can just use this. Okay, and so that's one way of handling evaporation. Another way of handling evaporation is to assume it's diffusion limited. And so we're gonna go into much more detail of that on that assumption later on. But the crux of that assumption is rather than using this expression here to compute the production rate of the vapor, we instead assume that we assume that the mass fraction of the vapor on the surface is always at the fully saturated conditions. Okay, and so that basically means that the partial pressure of the vapor on the surface is equal to the saturation pressure. And so you can go through some step, and on your homework 3 you have this problem. You're going to show that under such conditions that where you apply the boundary condition of that the mass fraction of species I on the gas phase side is equal to the saturation conditions is basically what your condition is, and you wind up with this sort of nifty expression here for the evaporation mass flux. Okay, and so yeah, then if we use Fick's law, we can use we can reduce this further, where basically the diffusion velocity using Fick's law is some mass diffusion coefficient over yi times the gradient of yi. But here we only care about it at the surface, and so I'm just basically defining this to be the gradient of yi with respect to the surface direction at the surface. And so that's another common way that you'll see this being written. And when we describe multi-phase combustion of droplets and particles, this expression here will be used quite a bit. So I'm just sort of listing what they are, just so that if you're looking up in your notes and you ever need to look at how to handle a surface, all these things are in one spot. Okay, and so that's a fairly decent spot to stop for today, and we will handle momentum quickly on Monday, and then hopefully either on Wednesday or Friday of next week we will start working on we will start some applications on initiation theory. Okay, any questions?
So for the surface reactions, if you've got something that is like an end burning rocket motor that requires, I don't know, we would only care about the surface reaction if it needed something from the atmosphere in order to create the reaction?
No, you could consider, and again, when we do propellant combustion, we're going to go over this quite a bit, but say we have a burning stranded propellant, you can draw a little control surface on the surface, and here you would have, say, RDX going in, and going out, you have a whole bunch of different species. You would have a mixture of, God, what do you have? Would be, I don't know, I'd say Hono, all sorts of just reactive fragments, CH3, all sorts of goofy things. And you could think of what is basically turning this RDX, this solid RDX, into these gas phase species, which then turn around and burn, is some sort of surface reaction mechanism. Okay, or some sort of surface generation term. Okay.
Okay.
And so even in that context, you have surface reaction. You may not model them as formally as you would do for, say, a carbon particle, but it's still a sort of, you can still model it in Earth or think of it as a surface generation process. Now, for actual self-propellant combustion at low pressures, it gets really complicated because there is stuff going on inside of the surface on the condensed phase side. Okay, and by condensed phase, I mean solid or liquid, because what makes propellant combustion somewhat hard too is that it starts out as a solid, but it melts before it burns. So there is a melt layer that you need to contend with. But all those dynamics you will get into here in probably about 4 weeks or so.
Gotcha. Thank you.
Yep. Okay, any other questions? Okay, stop the share.